This lecture will talk about resonance. Resonance forms or resonance structures are Lewis structures with same atom placement but different electron arrangements. Now keep in mind that only electrons are moving, but you are not breaking any sigma bonds because that would change the identity of the compound. So when you draw resonance forms, you are just drawing different electronic arrangements of the same compound. Now let's try drawing the resonance form of this compound here. The first thing to note is that resonance forms are connected with a resonance arrow. This double-headed arrow implies that these two forms are in resonance with each other. It is not the same as an equilibrium arrow. Resonance forms are also usually enclosed within square brackets. Now if we analyze this resonance form of the original compound, note that only the electrons have moved. This is called delocalization. If you study this resonance form, you'll note that we have not made any new sigma bonds and we have not broken any sigma bonds. Remember, that would alter the identity of the compound, and we are drawing resonance forms of the same compound. The only things we're moving, therefore, are pi bonds and lone pairs. In this particular case, this lone pair on nitrogen has gone down here to make a new pi bond between carbon and nitrogen, and in turn, this pi bond between carbon and oxygen has broken to shift the electrons towards that oxygen. The reason that you have to break that carbon-oxygen pi bond as you are making the carbon-nitrogen pi bond is because of the octet rule. Remember that carbon can have a maximum of 8 electrons, and you cannot break that octet rule for carbon. Therefore, when you add in these two electrons from nitrogen, at that point you are giving carbon a total of 10 electrons. Not possible. Therefore, we are breaking this pi bond because pi bonds are weaker and easy to break, and we are moving it towards this oxygen. And now everybody's octet is fulfilled, and we have just moved around the electrons in the form of lone pairs and pi bonds, and we have got the resonance form. Always keep in mind that this resonance arrow is indicating that these two are resonance forms of each other. They are not isomers, they are not part of a reaction, and they are not in equilibrium. Now, individual resonance forms do not accurately represent the true structure of the molecule. So that's why we draw a resonance hybrid. Each of these resonance structures will contribute to what we call a resonance hybrid, and that hybrid will more accurately represent the structure and the electronic distribution in that structure. When we draw the resonance hybrid, we are going to draw the basic structure of the molecule, and then we are going to use dotted bonds to indicate where our electrons are delocalized. We note that we have a negative charge that is delocalized over these three atoms, oxygen, carbon, and nitrogen, and so we show that the electrons are moving between the oxygen, carbon, and nitrogen, and we show a negative charge to indicate that it's a negative charge that is being delocalized. Now, not all resonance forms are equal contributors to the resonance hybrid. When you're drawing resonance forms, remember that only electrons are moving. You are delocalizing lone pairs and pi bonds. All your resonance forms must be valid Lewis structures. They must have the same number of paired and unpaired electrons. When you're determining the major contributor towards the resonance hybrid, remember that filled octets are more important. You want to try and maximize the number of covalent bonds, and you want to minimize the separation of charge. In general, you want to put the negative charge on the more electronegative atom. Now let's go back to the two resonance forms that we looked at before. Let's analyze these two and determine which one is the major resonance form. That means which one is more stable, and therefore which one is contributing more towards the resonance hybrid. So now let's go back to our guidelines. First of all, we have to check and make sure that both of them, we've only moved electrons, and both of them are valid Lewis structures. Both of them have the same number of paired and unpaired electrons. That's standard. That has to be there in all resonance forms. Now let's look at the 3 guidelines to determine which one is the major contributor. Here what you're looking for is you're looking for the more stable compound. If it's more stable, then that's more accurate of a reflection of that resonance hybrid. Okay, so now let's look at filled octets. So in both these structures we have filled octets, so we don't have any distinction that way. If we look at maximizing the number of covalent bonds, well, in both cases we have the same number of covalent bonds, so there's no difference that way. And now let's look at minimizing the separation of charge. In this case, again, we don't have a difference in the separation of charges, but we do have a difference in where the negative charge is placed. In this structure here, we have the negative charge on nitrogen. In this structure, we have the negative charge on oxygen. Now remember that oxygen is more electronegative than nitrogen, and therefore oxygen is going to be more capable of stabilizing this negative charge. That would mean that this is the major contributor. So this is the major contributor to the resonance hybrid, which means that this resonance structure more accurately reflects what the true structure of the compound is than this structure here. So in that case, why do we care about drawing the structure at all? Well, the reason is that this structure is going to help us explain reactivity, which this resonance form may not help us do. So while both of them are going to resemble the resonance hybrid, remember that this one is the major contributor. As far as reactivity goes, this one is telling us which one is more stable. This one is telling us which site is actually more reactive. And so when you go later on into the course, you will come across nitrogen. And when nitrogen has a negative charge, you will notice that it is going to be more reactive than oxygen having a negative charge. That's the importance of being able to draw the minor resonance forms as well as the major resonance form. Now let's look at some examples. This is the first example that we look at, and what I want you to do is figure out the resonance form for this compound. If you're not completely comfortable with line angle drawings, this is the line angle drawing. If you're not comfortable with these line angle drawings yet, I would recommend that you convert them into Lewis structures. Or what you could do is just fill in all the hydrogens to make sure that you are not inadvertently breaking any sigma bonds. Here I've drawn out a partial Lewis structure, so this implies that there is a carbon at each of these vertices, and I've filled in all the hydrogens already. What's important here, of course, is this region here, which shows that carbon is going to have an empty p orbital. Remember that this is a carbocation. It's got a positive charge on the carbon, which means that it would like some more electrons. So keeping in mind that you can accept electrons here, look around in this molecule for anything that can donate some electrons. The pi bond here, this pi bond is what's going to donate into this empty p orbital here. So if we were to draw arrows, we would show that these electrons, this pair of electrons here is going to move to make a new pi bond here, and that would satisfy this carbon's positive charge. So if we draw the resonance form, filling in carbons as well as hydrogens, we've got this methyl group that is unchanged. We then have this carbon, which has one hydrogen here. And this is where we broke this pi bond. So we're going to leave it as it is right now. I'm just going to fill in the CH3 and not draw them all out. And finally, we've got what was originally our carbocation. So this is where we originally had the positive charge. Now because we've moved this pair of electrons over, we've got a double bond here. So this is where we formed the new pi bond. And because now this carbon is no longer with its full octet, we've got a positive charge on this carbon. So always remember that the overall charge is going to remain the same. This compound has a positive charge, therefore this compound also has a positive charge. Overall, it has one positive charge. You've only moved pi bonds, and in this case you didn't have any lone pairs, but you had an empty p orbital to move those electrons into. Let's look at this example. Now this is the line angle drawing. If you're not comfortable with it yet, we can go ahead and fill in all the hydrogens. If you want a full Lewis structure, remember you need to put in each of these carbons at these vertices. Right now for clarity, we're going to leave these carbons as is, and we're going to just fill in the hydrogens so that we know where they are and we know not to break any of those sigma bonds. For clarity, we're also going to put in the lone pairs of the oxygen, and we know that this negative charge implies an electron pair here. Before we draw the resonance forms, I want to talk briefly about the curved arrows that we've been using so far. Now, previously we used curved arrows to show the movement of electrons in resonance forms. Curved arrows are very prevalent in organic chemistry, and what it means is it's the movement of two electrons from one atom here towards another atom here. So the base of the arrow always indicates where the electrons are coming from, the electron-rich site, and the head of the arrow shows where it's going to. The double head specifically refers to two electrons. Now if you were to think about the resonance form again, so let's go back here. If we were to think about the resonance form, we're going to start from this electron pair here on this carbon. We want to delocalize it and see if there are any resonance forms possible. The first thing we do is we start drawing our arrows and see if we can take it anywhere. So starting from where the electrons are at, we can make a new pi bond between these two carbons here. As we make a pi bond here, we are exceeding this carbon's valency. We cannot do that, so that means we have to break a bond from this carbon. And that's going to be this pi bond, which is going to push the electrons onto this carbon here. So if we were to draw the resonance form, first draw the resonance arrow. Nothing has changed in this part of the molecule, so let's just draw that as is. And put in the lone pairs for the oxygen. This is your methyl group, remains untouched. And this is where we've got changes occurring. So I'm first drawing the skeleton and putting in all the hydrogens because I know that hasn't changed. Here is where I've made a new pi bond, so I'm going to put that in. And here is where I've got this electron pair, and I'm going to put that in, and that's going to be a negative charge here. This is our first resonance form. Now we can go one step further and push these electrons to form a pi bond here and push this pi bond electron pair towards the oxygen. This is similar to our very first example. So now if we draw in the arrows are going to start from where the electrons are, show where they're going, which is to make a pi bond here. So note that it's actually showing that it's going towards the center of this bond, that is making a bond. And then the electrons from this bond, so you start from the center of this bond, those electrons are going towards this oxygen, okay? And we can draw the last resonance form. In this case, we've got a single bond to oxygen, we've got 3 lone pairs, negative charge, nothing happened to the methyl, we've got a new pi bond that we formed here, so we can put that in. We still have this hydrogen here, and nothing has changed in the rest of the molecules, so we can just draw that out. And these are your 2 possible resonance forms.